Hello everyone, I'm Kevin, and for my senior presentation I will be doing my company Schmidt works. But before we start on that, I gotta tell you guys a little bit about me. I am currently in the graduating class of 2025 for the interview. I also was introduced to cars and engineering at age 13 whenever my dad brought me home a project car fixed for myself. Nice little introduction. My family has quite the history in engineering. In fact, my great uncle is responsible for part of the International Space Station, which might be floating above us right now. Additionally, I have quite a bit of SolidWorks experience at Grandview. My SolidWorks experience at Grandview entirely totals to, I believe, 3 or 4 classes now, where I've attempted to do almost any engineering possible. Finally, I'm SolidWorks certified. Now, I have my CSWA and my CSWE. Unfortunately, I never got to getting my CSWE. However, I do plan on getting it in college. And the college I plan on getting my CSWE within is Iowa State. Coming this fall, I'm going to be attending Iowa State to study a degree of mechanical engineering. Anyways, enough about me. We're going to go on to my expert advisors. Now, most importantly, my experts, Devin and Pham to be specific, have been the most crucial part of this project. Devin is about as qualified as you can get to help me with this project, as he is the lead and head captain of Global Formula Racing. Now, Global Formula Racing is one of the top racing teams in FSE in the world currently, as they have headquarters in Germany and as well in the United States of Oregon. Therefore, Devin is about as qualified as it gets for this project. Devin knows everything, and he has been able to help me with any question I have, no matter how stupid it gets. Now, moving on to my non-experts. Of course, we have to have these, and of course, they have been helpful. First of all, we have Jack Post, my literary support. Mainly, he's gotten me through the struggle of writing the journals, one of my least favorite parts. However, without him, I think I probably would have had another 1,000 misspellings within my project, so very important. Second of all, with this lovely photo, we have Colton Stranger-Torsen. Now, Colton Stranger-Torsen has been probably the most crucial non-expert, as he's gotten me through the struggle of SolidWorks. Now, for you guys who don't know what SolidWorks is like in dealing with SolidWorks, it's a pain. The whole thing likes to crash every 5 seconds. In fact, it tried to delete my project halfway through my year, so it's always a struggle. And finally, of course, can't forget Kyra Olofsson. Kyra Olofsson has been helpful to this project in the fact that he is basically an encyclopedia of racing. You ask Kyra pretty much anything you need to know about racing, and Kyra will be able to tell you. Alright, so you might be wondering by now, what even is my project? Well, my project is focusing on 3 large main things. First of all, I'm going to be completing a large-scale CFD study, a computational fluid dynamics study of a formula student car. Now, I'm going to also be using this computational study to calculate for lap times of this car. By creating my own model, I'll be able to calculate for lap times around this. This is a skid pad event for the Formula Student Racing. Now, what a skid pad event is it's a simple figure 8 event where you take the track time of going around this figure 8 twice, and you see what is your best time going around a circle 1 time. You average it out, and the best time is your overall score. That is what I'm going to be accomplishing. And finally, of course, also I would like to learn quite a bit about aerodynamics, as one of my goals in life is to become an aerodynamicist. So, what are my project inspirations? What really inspired me to do this? Well, I've always loved racing, and I've always kind of been curious about aerodynamics myself. In fact, my car has a spoiler on it, and I've always kind of thought, well, how does that even work? So, learning aerodynamics kind of came naturally to me because I see it all around me, and I've always wondered how it worked. Secondly, I always wanted to join an FSE. Now, when I say always, I don't mean like Kyra, where he was 18 months old when he got into NASCAR. I mean more like during high school. I've wanted to join an FSE team since I started high school, as it is one of the best introductions into racing that you can get. So that's my second project inspiration. Finally, most importantly, is being told not to by Miss Lujan. I remember vividly walking out of my junior year on the final day and explaining to Miss Lujan how I'm super excited to do a senior capstone project. To which she asked, well, what do you want to do for your senior capstone? And I told her I wanted to make a go-kart. Well, this isn't quite a go-kart, but it's quite similar, and here we are. So, another thing that's important to cover is exactly the engineering required to make something like this. Of course, I must cover these bases because it's important to know what you need to become to make accurate models for this. So what you basically need to be to create an FSE car is an aerodynamicist. Unfortunately, I am not one. But what even is an aerodynamicist? Well, an aerodynamicist is someone who, as the name implies, studies the movement of air or the study of flow of air over objects. This could be trains, planes, boats, even buildings sometimes. The qualifications to become an aerodynamicist effectively sums up to be either a mechanical engineer or an aerospace engineer. Now, of course, you can be other forms of engineering. However, these are the two most common. And oftentimes, you'd also find these guys in the wild working on pretty much anything racing. These guys love racing. However, again, there is quite a few aerodynamicists who work outside the field of racing, as we need aerodynamics for pretty much anything that moves. Now, again, for me, I am not an aerodynamicist, unfortunately. However, I do have some experience that allows me to get into this project. My first and most important being, I know SolidWorks pretty well. My SolidWorks experience allows me to model anything I need to model for this project. Secondly, the most successful part is being able to access the internet and YouTube for my project. This has been crucial for my project, as it's taught me basically everything I need to know. Because unfortunately, I don't have the money to hire my own tutorage team here, teaching aerodynamics. And finally, of course, having a great advisor has been a massive help to this project. So, to get through a final thing, my project objectives. Before we get into the actual project, I must go over what were my initial goals for this project. Well, for starters, I wanted to create a full-scale FSE. I wanted to design something of my own rather than just taking a random race car off the internet, which was first what I was told to do. And I would like to make it my own, to test it on my own terms. Secondly, I'd like to kind of understand aerodynamics as it is. I'd like to get myself into the field of aerodynamics and really just have a grasp of aerodynamics. I'd also like to use these aerodynamic connections to make connections with FNSAA members. Now, of course, most FNSAA teams you can just join without needing a requirement. However, the more connections I can make, the better, as it might be able to get me into maybe Formula 1 or Formula 2. Also, I would like to improve my skills with SolidWorks. As Colton probably remembers, my skills starting off the year were pretty rusty. However, this project has helped me revitalize anything I've learned from SolidWorks and teach me quite a few new things about the program that I didn't know. Finally, I'd like to improve my public speaking skills. My public speaking skills, like some of the other guys who mentioned the public speaking skills, have been pretty lackluster. However, here we are, here we're doing it now. Alright, so before we actually get into the main bulk of my project, I'd like to give you guys a little bit of a crash course on aerodynamics. Now, of course, I can't teach you everything about aerodynamics, but I can teach you the simple basics of aerodynamics to help you understand my project better. These three simple basics I will be covering are the study of airflow, the principles behind this, and finally, the effects behind the principles. So, of course, starting with the study of airflow. What even is the study of airflow? Well, as the name implies, the study of airflow is the study of moving air. Luckily, we are in modern times where we're able to use CFDs, where we're able to calculate all our airflow over computers. However, in older times, they would commonly use smoke airflow tests, and they would have to do lots and lots of math. Again, we're in modern times, so I was luckily able to save myself some time not doing it. Secondly, the principles. We're going to start with Bernoulli's principle, as Bernoulli's principle is probably the most important for this program. Bernoulli's principle essentially establishes that air is pressurized. We know that air likes to move around on top and below objects. So, by using this, we can establish what creates lift and what creates downforce. The best way to think about it is air likes to stay at a constant state. If you increase the pressure of the air, well, it will push back on you. And if you decrease the pressure of the air, well, it would like to pull back on that as the rest of the air tries to flood it. So using this understanding, we can create a simple wing, which where it's low pressure pulls up on the wing, and high pressure pushes up from the bottom. Flip this upside down, and you have downforce. Downforce is effectively lift, but of course upside down. Now again, downforce is another subsidiary of Bernoulli's principle, and so is drag, which is why Bernoulli's principle is very important. Drag is effectively a perpendicular force of downforce. If we know what downforce is, we can know what drag is. Drag is like downforce, except it comes from the front and pulls from the back. Finally, we have our effects. Now, of course, there's plenty of effects to go over, but the three main effects I would like for you guys to know are the Koyana, Venturi, and ground effect. For starters, the Koyana effect basically establishes that air likes to stick with itself. It likes to be with its friends and kind of stay in a steady layer with itself. So we know that if you put a wing through the air, rather than the air flinging off the wing like it's going off a ramp, it likes to go over the surface of the wing and hug that wing. Second of all, we have the Venturi effect. Now, the Venturi effect is only utilized a few times. However, it's important to know that the Venturi effect is what happens whenever you squeeze air into a tight space. Think of it like when you were a kid and you put your thumb over the end of the hose. The water would go super fast out of the hose because as you squeeze the pressure increases and so does the velocity. That is the Venturi effect. And finally, the ground effect. Now, not to be mistaken with the airplane ground effect. The race car ground effect essentially establishes both the Koyana effect and the Venturi effect. We know that if we can get the air moving fast and squeeze it together and then rapidly remove it from the bottom of the car, it will create a low or high pressure area, low pressure area, which will suck the car to the bottom of the ground, allowing the car to have much better downforce. Effectively, we're trying to create a vacuum below the car. Finally, one little quick tidbit, I'd like you guys to know a little bit of slang as I will be using some of these terms. Now, our first word is wings. It's important to know this is a wing. This is not a wing. This is a spoiler. What a wing does is it actively works to create downforce, whereas a spoiler actively works to go against lift. So it's important to know this is a wing, that's not a wing. Second of all, track/wheelbase. For all intents and purposes for the rest of this project, just assume this is length and width of the car. And of course, finally, aero package. Aero package simply just means the wings and body of the car. It's anything that generates downforce. All right. Moving on to the beginning of my project, I'd like to introduce you guys to my lovely initial timeline. Now, I was quite overambitious creating this timeline, and I decided that I was going to make a full-scale model, which, unfortunately, I never ended up making a full-scale model. As you guys can tell, I probably wouldn't be able to fit inside this model. However, I did end up beginning with my research, but we will come back to this time, as it essentially establishes what I began with the 3D modeling and then finish with construction. To get us through this, as some of you guys see, I'm going to go ahead and add a timeline on the side. This way you can see the progression of time as I go through my project. Starting off, what is my research for this project? Well, research is important to know, and research is important to do for this project. However, as I got into the research, I found it to be a little confusing. It got kind of complicated kind of fast. Aerodynamics is a much more complex field than I ever thought it would be. So I went ahead and simplified a few things. I decided my three main questions I'm going to ask myself to research are, what are the required aerodynamics and what is necessary for this car? Well, some of the required aerodynamics are simply just for wings. We know with the wings we can generate downforce and we can generate all the forces required to study it. However, some of the non-required stuff is such as the steering columns, the suspension, and other components that are outboard components. These components do not generate downforce, unfortunately. However, they do create a lot of drag, and they do waste a lot of time 3D modeling. Therefore, to save myself some time modeling and generating, we're going to go ahead and look at those. Second of all, we're going to go ahead and look at max downforce, min drag. Now, of course, the most important part of figuring out this project is figuring out how much downforce my car could produce. And this is done by figuring out what's the maximum of downforce with the smallest amount of drag. Unfortunately, I can't just make a wing that creates thousands of newtons of downforce, because that would result in a lot of drag, and the car would end up being slow anyways. So I need to find a nice little medium between it. And finally, what is the end goal? Well, as described earlier, my end goal is to make a full-scale FSCE model and calculate the lap times behind it. That ended up taking 1 month off my time. So we're still pretty on track. Secondly, I decided to start with some bare-bone basics. I decided if I'm going to get this project started and create some 3D modeling for this project, I might as well do some basic stuff. So I started, with a simple shell, doing the wheelbase, and doing a regulation layout. The regulation layout is just simply the layout required by FSAE within their rule book, and just kind of laying out where stuff needs to be. Then I decided, well, since I'm ahead of time, I might as well start on some aerodynamic devices. Now, the first aerodynamic device I started with, I thought would be the simplest. Unfortunately, it was not. The nose cone ended up being one of the most complex aerodynamic devices I've built because, unfortunately, I really didn't know what I was doing when I was creating it. The way I decided to create it was, instead of doing a simple model and then correct the issues with it, I decided to create roughly 20 models and see if I could just make a model that would be perfect off the cuff. Granted, this didn't work at all, and this chewed into another 2 months of my time. So, I finally found a nose cone that did actually fit my project. And this final nose cone that did actually fit my project, I thought looked pretty great. In fact, I had quite a few people look at it and go, that would work. And in fact, I had some of my advisors think it would work. However, I re-went through all my research, and it turns out this nose cone would be more effective upside down. Really unfortunate. So I went back to the drawing board and created yet another nose cone. The lovely nose cone Mark 20. This ate another month of my time. So I had to go back and re-look at my timeline, because by this point, I had needed through 4 months of my timeline, and I'd only really covered 2. So I was way off track, and I needed to reissue how I would do my project from now on. So moving forward, I decided to get rid of the construction and instead focus solely on 3D modeling and lap times. as having a physical model is not nearly as important as having a working model. So to begin with my next stages, I also decided to increase the amount of time that I could use for each wing. Instead of just kind of trying to speed through it and make a model, I decided to make one simple model and refine it as much as possible. Now, this refining effectively slowed down or sped up the time process for which I could get through the models, because it takes a lot less time to make one model and make it better than it does to make 20 models and see which one works best. Of course, I had to start with the front wing, as the front wing is the most important model for a car. The front wing is the first thing to move the air over the car, and therefore, if you perfect your front wing, you can easily perfect the rest of the car. So for the front wing design, I decided, again, to do the incremental design. I started with a simple ramp, and I kept improving and improving and improving and improving. And from this improvement, one of the top designs I found that worked was a staggered cascade design. Now, what a staggered cascade design is it's simply stacking wings on top of each other. Now, why would we do this? Well, as established earlier, we have drag. And one of the ways to alleviate that drag is by letting some of the air through. So as you can see, by letting the air through, the air still moves steadily, but it also still goes up with the wing. If we were to just do a simple wing with no holes in it, well then the wing would probably create a large amount of drag, as the vacuum created behind us would pull the whole front end backwards. Now, another part of alleviating this drag was dealing with the tires. The tires were one of the hardest parts to figure out. Alleviating the drag created by the tires is an issue because due to the rule book's limitations, I cannot create a wing that goes over the top of the tires or create a wing high enough to fling the air over the top of the tires. So I decided to use the Venturi effect. By utilizing the Venturi effect, what I did was I created a small inlet on the bottom of my outer wing that allowed air to speed up and pressurize as it was exiting towards the tire. Then I increased the height at which this air exited, and therefore it had high pressure air going almost vertical into another stream of air. Therefore, this high pressure air was able to push the air over top of the tire and eliminate any drag from the tire. This was the final result for the wing, which ended up turning out pretty great. This ate 1 more month of my time. We're getting pretty close here. So, next I had to deal with the mid-body. Now, the mid-body is most likely one of the most simplistic designs you can do for this, as unfortunately due to the rules and regulations, you can't really make a whole lot with the mid-body. There's a lot of height restrictions and a lot of space restrictions with both the wheels and how you design it. So I decided to focus on 2 main things. One, I decided to focus on seeing how much I can introduce the ground effect with the rules allowed. And I also decided to see how much drag I could reduce by adding a wing over the top. Now, the ground effect used, unfortunately I couldn't do it like most race cars do, where they use a spoiler to get the ground effect to go up, as it just exists as a flat blade. Therefore, my attempt to do ground effect was to try to get the air to go as fast as possible underneath the car by using the nose cone shape, and then having that air separate out from the sides of the tires, which is why you see the wings out here are sticking much further out. That way the air sort of peels off the rest of the car. And of course, drag reduction. This time I actually had a little bit more height, so I decided to make a simple wing just to let the air go smoothly over the top of the tire so I wouldn't have to worry about the air. Finally, the last important part about my project, the rear wing design. Now, the rear wing design is pretty complex as well, as you have to deal with the driver. Unfortunately, you don't just get steady airflow, but rather you get a lot of turbulent tempo. So therefore, you have to kind of make an aggressive attack for your rear wing. The best way to do this is to maximize the size and increase the pitch of the wings, and that allows you to increase the aerodynamic downforce on this wing. Now, of course, I had to go with the staggered cascade design again, as the staggered cascade design proved the most effective with the front wing, so I decided to reuse it rather than see if anything else worked better. Again, staggered cascade design is proven. And secondly, the sign limitation. As I explained, I have certain limits from the rule book. The rule book likes to mess everything up on this project. So I really just could make it as big as I possibly could to make as much downforce. However, I couldn't make it that wide, so it ended up looking kind of goofy. This saved 1 more month off my time. Finally, I had all my parts together. So I decided to put them all together, and I kind of sat there and looked at it. And I thought, well, I think it's missing something. So I decided to color it. I thought I might as well make it pretty. And overall, it turned out pretty great for what it's worth. This car was a lot better than how I thought it would look going into the year, and definitely a lot better how I thought it would work when I was stressing about time halfway through the year when I wasted so much time on a nose cone. And luckily, it turned out pretty well. Now, for the final thing, of course, I had to go over the math. The math was the only way I could get the lap times, as I can't just simulate a car going around a corner without doing any math. Now, the way I did this math initially was I asked my expert advisor to provide me a simple formula to create this math. However, he did not provide me a simple formula, and the non-simple formula that he provided was a little unrealistic, and it never really worked. Some of the original times I was given were faster than the speed of light, which unfortunately is not very realistic for my car, and it caused me to have hours and hours and hours of delay trying to figure out how to get his formula to work. Finally, I sort of gave up on his formula and decided, you know what, I can make my own formula. The formula I decided to make was a simple lateral force formula. I knew that if I want the car to go around at the maximum speed possible, it has to be achieving the most amount of lateral force possible. Therefore, I rewrote the entire formula, solved for a number, and solved for velocity. And finally, I was given a more reasonable number of 11.84 meters per second. Now this time I then used to find the distance traveled, and then I calculated for how fast that 11.84 meters per second would get me around the track. Now, initially I thought, wow, I've made an incredible product because this timing ended at 5.04 seconds around one track length. And that would be a world record by quite a few seconds. Unfortunately, I forgot to consider something. Things I forgot to consider were the fact that my car does not have outboard components which do not create drag. Therefore, to create a little bit more realistic of a model, I decided to add drag to the car and add half a second to my car to give it a more realistic time. This more realistic time ended up being 5.5 seconds, which landed me closer to 30th place. This 30th place, of course, is not as great as some might think, but for me, this is a huge accomplishment, as even getting 60th place within this event shows that I can compete with actual colleges, where those actual colleges have teams of 10 to 20 people working on aerodynamics who all know how to use aerodynamics, where I had to teach myself how to do aerodynamics, model the car myself, and also I had to create the aerodynamic calculations myself. So with that, I deemed my project a massive success, eating up my final month and getting rid of that time limit. Oh, no, I'm just kidding. I finished with my bibliography, and that's it. Any questions? Yes?
Is the person going to add drag ball, and how is it going to affect the aerodynamics?
The person sitting in the car will add a bit of drag, and the most important aerodynamic effect they have is they cause a lot of turbulent air to hit the ring. However, the drag they do create is pretty negligible to the time, as they are not nearly as big as the rest of the car. The person I modeled for this was just a simple sphere, which after consulting my expert advisor, he agreed that a simple sphere would model perfectly for what I need. So effectively, a person would add a bit of drag and would affect the aerodynamics a bit, but not too much. Yes?
So I know that SolidWorks and Onshape are both capable of doing simulations where you're able to simulate drag and the total force that you have over a certain amount of time. Did you run the simulations?
I ran the simulations to garner the downforce. However, for some reason, SolidWorks refused to give me a drag calculation, as it kept giving me drag numbers that were kind of unrealistic. The drag numbers it were giving me were, sometimes it would give me numbers in the couple of hundreds, and sometimes it would say, your drag is 27 newtons. I tried and tried and tried to get SolidWorks to work with me, but for some reason, SolidWorks threw a fit every time and just gave me a random number for drag. However, for downforce, I did actually produce a downforce of 250 newtons at 50 miles per hour, and it kept giving me that number over and over again, so I do know that number is still fine. Yes?
What about the weight of the car? Are the intro components stacked things or was it?
So the weight of the car, unfortunately for my model, I am not modeling any outboard components, and I'm also not modeling any of the materials of the car. So to accomplish the calculations for the weight, I decided, and after consulting my expert advisor, to just get a general average number. After looking at quite a few numbers for the cars I'm competing with, I decided on a weight of roughly 400 pounds, and I also decided to add in the driver weight, as the driver weight should be included, and I said, well, I'll drive the car. So I got an approximate weight of 600 pounds of vehicle. Yes?
Would a headrest for the person affect the aerodynamics at the back of the car? This is going super fast and like dragging back.
Within this model, the skid pad event in itself, the car does not accelerate fast enough for many of these the outboard components to affect the model that much. However, in a lot of real models, there is some semblance of a headrest. As we saw with some of the other photos, there's a loop that goes over the driver's head for the driver's safety. However, again, I chose not to model these things as, since they sit right behind the driver's head, they don't add much of an effect to the drag at all. Like, the time difference would probably be in the millionths of a second if I were to add that to the drag effect. Yes? Are you guys here?
So when you were deriving your equation, did you touch like the Navier-Stokes equations at all, and like solve it for an initial value? Or was that just like modeled after what you saw?
Can you speak up for me, please?
When you derived your equation, did you use like a initial condition with the Navier-Stokes formulas? Or did you do like an approximation using the data that you already had?
I more or less did an approximation using the data I had. And I also assumed a lot of stuff, such as I assumed that the driver would be doing a perfect lap, and I would also assume that the airflow would be in a steady state airflow situation. So that took away a lot of the complexities of calculating a lot of the aerodynamic components, and that probably saved me a month or two of time. Yes?
If you had to say, how accurate would the time you calculated be compared to if you actually built this thing recently?
If I were to say, are you asking the initial time calculation of 5 seconds or the added calculation of 5.5?
The added.
The added one, I would say, would be about 85% accurate if I had to guess, as aerodynamics, unfortunately, is not in a constant steady state. If only air could blow steady all the time. However, this is not the case. Air is turbulent all over the place. So I'd say the numbers would vary quite a bit. However, they wouldn't vary dramatically. I think if I were to race this car, it would probably either go a little higher into 25th place or a little bit lower into 40th place. But the variation wouldn't be too extreme. Yes?
Do you think you realistically could build this car?
Given enough time, money, and resources, I think yes, I could build this car. However, it probably would have costed me a couple of $1,000s to make a full-scale model, and I'm one person, so this probably would have taken me a year or two. Anyone else? Yes?
So I noticed you have the really big wing on the top, and it's super tall, because if I remember correctly, you can't go wider because of the rules.
Yes.
But how does the weight affect the center of mass?
So the weight of the rear wing, most of the time whenever they model these cars or whenever they create actual physical models of these cars, the weight of the rear wing does not affect the overall center of mass of the car too much, as a lot of these components are made out of very lightweight materials. So the overall weight of the wing does not really tilt the car up, as I think what you're asking. However, it would have a little play, but it would most definitely be canceled out by the rest of the aerodynamic components further up in the car. Yes.
How would the outer panels of the wing affect it if there's wind blowing the opposite direction? Like would
Say that
that?
again a little louder.
Huh?
Can you say that again a little louder?
How would the outer panels of the rear wing? How would that affect the aerodynamics if you're making a turn?
So the outer panels of the rear wing allow the car to be stabilized front to back, and it effectively works the same way like a plane does. If you've ever seen a plane, which I'm sure everyone here has, it has a large vertical tail wing, and that's just to stabilize the horizontal air going across the car. By adding large vertical tail wings, this car can stabilize through the corners a lot better. Even though the air will be attacking it at a certain angle, it does provide the stability, because this car is not doing a 90-degree turn, it's doing a much lighter turn. So it will take away a little bit, but what it takes away is completely overcome by what it adds by being a vertical stabilizer. Yes?
So you said you're going to the University of Iowa.
Yes.
Do you plan on joining? I believe they have an F1 team. Do you plan on joining them?
Iowa State, and yes, I'm joining their FSA team.
Okay, good job. Thank you.